Hi everyone, welcome back to Chem Help ASAP. Today we are going to dive into quantum numbers. Now, if you watch my playlist on the history of atomic structure, you know that the quantum numbers came from solving Schrodinger's equation, and there are four of them: N, L, M sub L, and M sub S. Now we are going to unpack each of these quantum numbers and show how it relates to the electron in the atom.
We will start with n, which is called the principal quantum number. Now, n gives us the size and the energy of the orbital, or as we'll see sometimes, multiple orbitals. The values for n start at 1 and simply count up from there. Now, the larger the size of n, that means that your orbital is also larger in size and has a higher energy. And oftentimes, n is referred to as the orbital shell, or just simply the shell. Now, depending on your periodic table, you may notice on the far left that there are numbers that are in front of each row or each period on the periodic table. Those are the values of n for those rows. L is our angular momentum quantum number, and it determines the shape of the orbital. Now, its values go from 0 to n minus 1. Now, each value of L is assigned a letter which refers to the type of orbital. So let's run through our values of L, and I'll show you the pictures of what the orbital looks like. So we'll start with L equals 0. That is called the s orbital, and its shape is a sphere. So here is a picture of a sphere. Pretty simple, right? Okay, let's go on to L equals 1. That is called a p orbital, and that orbital has two lobes. So you can see in the pictures here, these p orbitals each have two lobes. Moving on, if L equals 2, that means we're talking about d orbitals, and these generally have four lobes. So you can see the pictures of the d orbitals here. You'll notice there's one odd one out here that actually just has two lobes. Finally, if L equals 3, that means you're talking about the f orbital, and it has multiple lobes. So if you look at the picture of the f orbitals, you'll notice that some of them have 4 lobes, some of them have 8 lobes. You've got this guy, which actually only has 2 lobes, so these start to look a little bit different here. Now, m sub L is the magnetic quantum number, and it is going to give us the spatial orientation of each orbital. Now, its values run from negative L to L. So let's go back and take a look at our value of L and see what that means for our values of m sub L. So if our value of L is 0, that means m sub L only has one value, that is 0. Of course, that is the s orbital. Its shape is a sphere. So again, you see this picture of the s orbital, and you will see that there's only one orientation because, of course, a sphere is symmetrical. It doesn't matter how you rotate it in space, it's going to look the same. Okay, but let's move on to when L equals 1. Now, when L equals 1, m sub L can have 3 different values, and that is negative 1, 0, and 1. Now, again, when L equals 1, that's the p orbital. It has 2 lobes like we saw before. But if you look again at the picture for the p orbitals, you will see that there are 3 different orientations. We have px, pz, and py. And of course, the x, z, and y simply refer to how the lobes are oriented in space. You can see for the px, the lobes are oriented on the x-axis, as opposed to the pz here, where the lobes are oriented on the z-axis. So the p orbitals have 3 different orbitals depending on how it's rotated in space. we can apply this to the d and the f orbitals. So if our value of L is 2, you can see here is our range of m sub L. It has 5 different orientations. And again, if you look at the picture for the d orbitals, you can count them up. There are 1, 2, 3, 4, 5 different d orbitals, and they're all oriented in space differently. And the same, of course, is true for the f's. This time our value of m sub L runs from -3 to 3. That means we have 7 different orientations. And again, if you're looking at the pictures of the f orbitals, you'll see that there are 7 different orientations for the f orbitals. This last quantum number is m sub s. It is called the electron spin quantum number, and it simply specifies if the electron is spin up or spin down. Now its values are -1/2 and 1/2. Now you might remember from a previous playlist when I talked about the history of the atomic structure how m sub s was actually added later, and this is because each orbital can hold 2 electrons, but each electron must have a unique set of quantum numbers. Therefore, they had to introduce just one more quantum number because when 2 electrons are in an orbital, they do have different spin states. They are both unique.
So you can now see how the quantum numbers give us an exact address for each individual electron. No 2 electrons have the same 4 quantum numbers. Now we are going to use these quantum numbers in our next video, and we're going to start working with electron configurations. Thanks so much for watching.
So if you look at the picture of the s orbital, spot.